Hi everyone, welcome back to Math 261. This is Scott. Let's get started. So, in the last section, we were getting pretty deep into the weeds of matrices and their invertibility conditions. So now let's take a step back and look at something different. So what we're going to talk about today is, and we're going to skip ahead a little bit in the book to section 2.8, where we'll be taking on a new topic, which is subspaces of Rn. Alright. Now, a warning here. So you have to be more cautious in this class than you have been in just about any math class you've ever taken before about the proper use of the different words that we are using here. So, subspace. Space in that is a word that is carrying a great deal of meaning, and essentially what it means is this. So space here. Space more or less refers to a self-contained universe. So space means a self-contained, you could say like universe. And that's with regards to linear stuff. So this is a linear algebra class, so linearity is the important thing here. So it means a self-contained universe with regards to linear combinations. And in particular, the two kinds of linear operations we can do are scalar multiplication and addition, and any combination thereof. So space means a self-contained universe with regards to linear combinations, and then the definition of a subspace so H is a subspace of Rn if, and then what we essentially have are three things. So, well, we have really, so it has to be a subset first off. So if it is a subset of vectors such that, and then what we have are three properties. Property number one, H has to contain the zero vector. Now, we are always going to assume whenever you just write a zero vector without any indication of size that it is of whatever size makes sense in this context. So this would be the n-dimensional zero vector, so n entries, all zero. Okay, so H must contain the zero vector. 2. For any U in H and V in H, the vector that you get by adding them, it's U plus V, must also be in H. So the term for this is that it is closed under addition, closed under vector addition. So H is closed under vector addition. So that's the phrase that's used here. And then thirdly, for any v in H and any c in the real numbers, so a scalar c, vector v, you might be able to guess where I'm going with this, scalar multiplication will still leave you inside the space. So CV is in H as well. So this is referred to by saying that H is closed under scalar multiplication. So in other words, if you are in H, you cannot escape by using any other means that is in H. As far as the vectors in H are concerned, they are a world unto themselves. They are stuck there. They have no inkling that there might be anything outside of it. So let's discuss some examples of subspaces so that we can know what we're talking about. So examples. Of subspaces. All right. First off, there is a subspace that is boring, and that is the entirety of Rn. It only slipped in under the radar by the fact that we set these laws in place, and it got through on a technicality. So the entirety of Rn is a subspace. So first off, the two boring subspaces, the trivial subspaces. So the trivial subspaces are, first off, all of Rn itself. So sure enough, if I were to take any two vectors of Rn and add them together, the result will be a vector in Rn. If I were to take any scalar multiple of a vector that is in Rn, it will be in Rn as well. And of course, the zero vector is a famous member of Rn. So we have Rn itself, which is basically it's taken the sub out of subspace, but technically the rules would classify it as such, and we as mathematicians are bound to respect the letter of the law, more so even than the spirit of it. So Rn itself. All right, then the other trivial subspace, the other boring subspace, is the set that contains the zero vector and only the zero vector. So if I take zero itself and I ignore everything else, then there's no way of escaping that tiny little universe. The tiny little universe unto itself. So this is the set with only the zero vector. If I were to take any element of this set, namely 0, and add it to any other element of the set, namely also 0, the result will be in this set, it will be 0. Similarly, if I were to do any scalar multiple of the 0 vector, I'm still going to have the 0 vector. So again, in a boring way, this turns out to belong to this turns out to fit the definition of a subspace as well. So these are the two boring ones. The one is boring because it's not sub anything, it's just the original world itself. And the other is boring because it's too small. It has no grit to it, nothing going on. All right, but in between these two extremes, that's where all the fun things are. So here are some other examples. So any span is automatically a subset. So any span of a collection of vectors is automatically is automatically a subspace. If I take vector 1, vector 2, vector 3, they're all the same size, and I take the span of those vectors, that is taking literally all the linear combinations of them. So everything you can make by adding, by scalar multiplying. And so essentially we have just made a set that by design fits exactly these conditions. So any span of a collection of vectors is automatically a subspace. So specifically then, what that means is geometrically we'll have the same examples for subspaces as we saw for spans. So specifically, we can then describe what these subspaces are going to look like based on what we already know about spans. So the subspaces will come in a variety of forms. First off, there's what we can call the zero-dimensional. The zero-dimensional subspace, which is just the origin. So the zero-dimensional subspace of Rn is just the origin itself. Then there's the one-dimensional subspace. And what this comprises is just a line through the origin. So the origin is always going to be an automatic member of any subspace because that's one of the properties that even defines a subspace, is that it must contain the zero vector, which is the origin. Now a two-dimensional subspace, and here we're going to always assume that Rn is a big enough world to contain these. So this is a plane through the origin. Again, this is all just exactly like what we were talking about with the spans. So geometrically, the span of one vector is a line that goes through the origin. The span of two vectors is a plane that also goes through the origin. And in fact, we can talk about a three-dimensional subspace, assuming Rn is at least R3. So you can refer to this as a three-plane, or you can refer to it as a space. So we'll say a three-plane, just so that the space doesn't get a little bit overcrowded in meaning. A three-plane through the origin. And same is true up to any arbitrary level, so k-dimensional subspace. So it's easy to say, hard to visualize. So the pattern just continues. Oops, sorry. It was same as it was, just with k in place of 3. So a k-dimensional subspace is a k-plane through the origin. Again, these things above 3 dimensions, really all we're doing is reasoning by analogy. We can't visualize these things. However, because we are able to apply the same techniques in so many different varieties of circumstances, we can still talk about them and they still make a kind of sense, even if it's not necessarily of the same geometrically intuitive sense that it makes for lower dimensions. But if you think about, for example, chemical equations, there the vectors are a pretty abstract thing. It's just like a catalog of how many atoms of this element, that element, and some other element, and some other element are involved in your chemical reaction. And so in that case, there's no real limit to how many dimensions we could be talking about. And then subspaces would there represent the possible universe of results that can come out from those specific ingredients that you're starting with. So the mathematical analysis would still be the same, even if it's not visualizable in the same way. And in fact, so we humans, we think our brains are very general in their spatial reasoning, but in reality, our brains are very, 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 very specific in what they're able to consider, and we are effectively limited by the survival constraints that went into our evolution, those many millions of years ago, that have given us a very, very specific geometrical framework for how we are going to be able to visualize things in the world. However, the whole point of mathematics is that we're no longer tied to those specific visual frameworks anymore. We can figure out what the patterns were at lower dimensions and extrapolate them upward to higher dimensions and use the same techniques, just more generalized. Now, at this point, I would like to actually bring up a kind of related and fun topic from literature. There's a book by Edwin Abbott, who was a Shakespearean professor in England in the 1880s, called Flatland. And what it deals with is it's an imaginary world that's all taking place on a two-dimensional plane. And the creatures that live on this world are just they're just little two-dimensional figures. So the males are all polygons, the women are all line segments, and then there's some social commentary regarding the upper and lower classes, the relations between the sexes, things like that. But anyway, everybody lives on this little two-dimensional plane, and so everybody's view from the world of the two-dimensional plane is of basically like the world around them being essentially like a little line segment, and based on how bright things are, they're able to determine the shapes of all of their neighbors and how far away they are, things like that. Anyway, everybody in this world is very adamant that that world is the whole world. There is no such thing as a third dimension, and certainly nothing beyond that. But then one night, the main character of this, who is a square and a mathematician actually in Flatland, he is visited by a creature from the third dimension, a sphere. And the way the sphere visits his world is just like as like a little ball, just kind of slides down through the plane that is Flatland. And as he does, the cross sections go from being just like a point to being a circle, to being a bigger circle, to being a smaller circle again. As the sphere slides down through the space, and ultimately the sphere's goal is to try to convince the little square that there's such a thing as the third dimension. And the square is skeptical, to say the least. And so, in order to help him understand, what the sphere does is takes him to a couple of other spaces. The first space he takes him to is like Point Land, which is just a little single point. And the only person who lives there considers himself basically the emperor of infinite space. He's just like the tiny little self-contained point. And then after that, they go to Lineland, where everybody is just little creatures that live along a line, like little line segments that are, it's like a train, kind of jostling back and forth around a line. Then up to Flatland, and then after that, they go up into third dimensional space, like Spaceland, I forget what to call it. And so the little square's mind is blown, his perspective is enhanced, and he comes back to Flatland and spreads the good news about the existence of the third dimension. And in fact, he even asks the sphere if there could be such thing as a fourth dimension. And the sphere is just as closed-minded to that as the square was to the third dimension, and it's all an amusing little bit of social commentary from the 1880s. And so here, for example, and it has like lots of explanation of how people see in this little world and what it looks like when they go to Lineland, or what it means when they cross through spaces shown by others. And it's just a fun little read. It's short. It's less than 100 pages, I think. Yeah, it's only like 83 pages, and it can be had for cheap. For example, I got this copy for $1. Anyway, it's a fun little book, and there are actually a couple of sequels to it. There's a book called Flatland, which is okay, I think, but my favorite sequel to it is this other book called Sphereland, in which they find out that actually Flatland isn't a plane, but is actually a sphere, and they had never realized that the space that they lived on was curved. And it's basically, so Flatland is more or less a metaphor for higher geometry, and Sphereland is more or less a metaphor for things like the general theory of relativity, in which we find out that space-time is itself curved. And these are both interesting little books to check out if you find yourself with a little bit of extra pandemic-related reading time. I especially would recommend Flatland. It's sort of a classic, and anybody who wants to be an educated mathematician ought to also familiarize themselves with the basics of mathematical literature. But anyway, back to the main thread of the conversation. So, some examples of subspaces we looked at were, first off, the trivial ones that went from the whole space down to just the zero vector. And then we could look at some spans of vectors within space. Now, if we focus our attention on a specific matrix, an n by n matrix, then there are, an m by n matrix, then there are two other subspaces we can associate with this matrix. So let's look at this. So column and null space. So the setup here is we're going to be dealing with a matrix, and A is just going to be an m by n matrix. And in this space then we are going to have, with this matrix we're going to have associated two subspaces of Rm on the one hand and Rn on the other. So then there is what is called column space. So column space of A. So this is the column space of A. And this is the subspace of Rm, that's R mic. The subspace of Rm spanned, or you could also say, or generated by the columns of A. So because A has m rows, that means the columns of A are each going to be n-dimensional column vectors, and then if we take those and we take the span of them, that will make what is called the column space. And then there is the null space, which we write null A, and this stands for the null space. And this is often written as one word, often written as two words. There's no standard form there. So this is the null space of A, and what this is the set of all vectors in Rn, so that's R November, such that, let's say all vectors are in Rn, we'll call them V, such that AV equals the zero vector. And that's why it's called the null space, because null, meaning zero, refers to the fact that these are the vectors who, when you apply A to them, will produce the null vector, the vector 0. So in other words, this is the set of solutions. So i.e. the solution set to the matrix equation AX equals 0. Okay, well that in itself gives us a little bit of a roadmap going forward for how we're going to approach these things. So since every span is a vector space or a subspace, we can also ask ourselves about whether we can find a set whose span gives any given vector space or subspace. And that is what is called a basis. Basis. So a basis for a subspace is a set of vectors that, and then we have two properties. One, so it has to do both of these. One, are linearly independent. And two, span the vector subspace. So in other words, the basis elements can be thought of as the minimum set of ingredients from which you can generate the whole space. So this is like the backbone of the space. So this is the minimum set. It's like the Noah's Ark set. It's the minimum set of vectors needed to generate the subspace by linear combination. So that's what the meaning of a basis is. In some ways, it is the sort of bare bones, most basic set that you could make that will still manage to span the space. So, when we're talking about all of Rn, then we can talk about the standard basis for Rn, and we've actually already seen what this is. So an example here would be the standard basis standard basis for Rn. So this will be the collection of vectors. We've already seen them. We call them E1 up through En, where E1 is the column vector that has a 1 in the first column and zeros elsewhere. E2 has a 1 in the second entry. This one has a 1 in the first row, first entry. This one has a 1 in the second entry. And so it continues until we get to the last of them, En. Which is zeros all the way down until the last entry, at which point it's 1. So this is a basis for Rn, the standard basis. And in fact, this is in some ways, the most universal basis that would be chosen for a vector space. But other bases can exist. Now, when we're talking about a smaller subspace, so what is called a proper subspace of Rn, such as the column space or the null space, then we have to do something special to find the basis, and that's going to be one of our main tasks here. So finding bases, it's the plural of basis, bases for call A and null A. That's the task. So if we want to find bases for the column space and for the null space of A, we can try to think about how this would work out according to our knowledge. So for the column space, of A, and by the way, so you can write these things with or without the parentheses, and the tendency would be to write them without if there's no danger of confusion. So for column space, the idea here is that you want to identify the basic columns, the basic variables of the space here, and you would do that by row reducing, and then all of the columns that contain pivots, those will be the basis for the column space. So the idea would be find the pivot positions in the reduced row echelon form of A, and then those columns of the original matrix will be a basis for column space of A. And that's why, turns out, so I didn't say this at the time, but that's why they are called the basic variables. The variables that correspond with these particular columns, it is because they form the basis for the column space of A. Now, what it means when you've identified a particular collection to be the basis, what it means is that, number one, they're linearly independent of each other, so no one of them can be made as a multiple of the others. And number two, together they will be able to make all the other elements. So, i.e., those columns are linearly independent of one another, but all the other columns can be made as linear combinations of those. So you've got a minimal set. It is in some ways the minimum viable set of all of the columns of a matrix. Now, as an example, let's take a sample matrix A, and here I'll do the hard work of row reducing for us. But we'll say the original matrix A looks like this: 1, 0, 2, 4. That's the first column. -5, -1, 3, 5 is the second column. 3, 1, 0, 5 is the third column. And 0, 1, 1, 1 is the fourth column. So we have 4 columns of 4 entry vectors. And then if we were to row reduce it, either by hand or by calculator, we would row reduce, row reduce, row reduce, and what we'd get is 1, 0, 0, -1. Take it from me, this is what you'd get. 0, 1, 0, 1. 0, 0, 1, 2, and then 0, 0, 0, 0. So then, if we look at this row reduced version of A, we will notice where the pivots are. So there are pivots in columns 1, 2, and 3. So then, what that means is a basis for the column space of A could be the set that contains column 1, column 2, and column 3 of the original matrix A. So column 1, and it's important here, we are talking about the columns of the original matrix, not the row-reduced matrix. We use the row-reduced matrix to figure out where the pivots are, and then that is where, those are the columns that will form our basis. 3, 1, 0, 5. And the proper formatting for a basis is, it is a set of vectors, so you should actually say with set braces, a set that contains this vector, this vector, this vector. Column 1 of A, column 2 of A, and column 3 of A. That's where these come from. And that's how you do that. So if you have a matrix, you would use the row-reduced form to identify the columns that contain pivots, in other words, the basic variables. And then those will form the basis of the column space. So there's that. Now for the null space, it's a little bit trickier. What you want to do there is you again want to row reduce. Row reduction is basically our one trick that we know how to do. So you will again row reduce, but we will row reduce in service of solving the homogeneous system of equations represented by AX equals 0. So to find the basis of the null space, what you do is this. So solve the homogeneous equation AX equals 0, and you do that by row reducing. In particular, you'd row reduce the augmented matrix, A augmented by zeros. Then once you've row reduced that, then if you get the solution in parametric vector form, and then those vectors, the vectors that are the ingredients of this, will comprise the basis. The vectors that make up the ingredients of the parametric vector form make up the basis. Now, as an example, let's again return to that A. And think about how this would play out. So if A is equal to 1, 0, 2, 4, negative 5, negative 1, 3, 5, 3, 1, 0, 5, and 0, 1, 1, 1. So if those are our vectors, make up A, then what we'll do is we'll do the augmentation, A augmented by zeros, which is the first step to solving the augmented system. So that's 1, 0, 2, 4, negative 5, negative 1, 3, 5, 3, 1, 0, 5, and 0, 1, 1, 1, augmented by 0, 0, 0, and 0. Then we would row reduce this. And just as we saw already, there'd be 1, 0, 0, was it 1, 0, 0, negative 1, 0. Then we'd have 0, 1, 0, 1, 0, 0, 0, 1, 2, 0, and then 0, 0, 0, 0, 0. Now thinking about this column represents x1, this represents x2, this represents x3, this represents x4. x4 is the free variable, x1, x2, and x3 are the basic variables. So together we can express each of the basic variables in terms of the free variable. So x1 minus x4 equals 0, which implies that x1 equals x4. x2 plus x4 equals 0, which implies that x2 equals negative x4. x3 plus 2x4 equals 0, which implies that x3 equals negative 2x4. x4 is free, so we could just say that then implies that x4 equals x4, which together then altogether lead us to the conclusion that x, the vector, which equals x1, x2, x3, and x4, that's actually the same thing as x4, negative x4, negative 2x4, and then x4, which in turn we can pull out the x4, use it as a parameter, so that's what makes it parametric vector form, of 1, negative 1, negative 2, 1. And then that means that vector right there. We only had one in this case, maybe sometimes we'll have more than one. This is the basis for null A, in particular, so we can say basis for null A is the set that contains it. 1, negative 1, negative 2, 1. So square brackets to indicate that it is a set, and it is a set of vectors, and those vectors are specifically just this one. Okay, so to recap, if we start with a matrix, a specific matrix, and we want to ask ourselves about the column space of this matrix, what we can do is find a basis for it by doing a row reduction, and then from that we can identify which variables are basic variables, and those columns of the original matrix will then make up the basis of the column space. So here it'd be x1, x2, x3 are basic variables, meaning column 1, column 2, column 3 are the basis of the column space. Conversely, if we are interested in the null space, then what we are interested in is the space of solutions to the homogeneous equation, and that in turn means we are interested not in the basic variables, and we're more interested actually in this case in the free variables, and we want the parametric vector form of the solution set, and the vectors that make up the parametric vector form will make up the basis for the null space. So important stuff here. The basis will always be a set that is associated with a space, and a space you can think of as being a span. It all, once again, it all becomes a rather delicate matter of terminology and language, but don't worry, the whole point of this course is to give you a chance to get yourselves nice and familiar with the foreign language that is higher mathematics. To learn more about this and how it connects with that invertible matrix theorem that we've been building up over the course of the last couple sections, come back to for the next episode of Math 261. Till then, bye.